I don't know what people do in a job. Um, am I going to be successful there? I've been getting good grades in education. Okay, what is going to be the situation when I'm in the job? Um, am I going to be successful there or not? So a lot of thoughts I had in my mind. You guys have a similar thoughts? How many share the same questions, fears, or dreams that I have in my mind? I just explained. How many of you share similar things? Even though 25 years gone, but I think it's the same sort of fears that we have for the unknown that comes in your life. That is where typically people struggle to guess that. But C mean create opportunities. You have to go out, you have to take risk, you have to create opportunities for yourself. Some people are very lucky, opportunities come their way, but most of us not that lucky. We have to create that luck, right? So the C I really want to stress with you that you need to go through some tough times. You need to accept some challenges. Doesn't matter how much uncertain future is, but you calculate some risk, you make some assumptions, and you set a reward for you, and you go for that. Okay, so first P is for passion, C is for create opportunities, and then HP. What is H? H is hard work. And what is P? Persistency. Okay, so this chip design, whether it's a career or whether it's a business, this is a game of patience. This is a long-term game. Uh, Sometimes we work hard, um, and something the result is not there, reward is not there immediately, and we get disappointed. But no, you need to learn from some of the things. Sometimes your direction maybe is not right. The way you're working is not probably right, and need to have some twist in that one to make it right. But you need to learn from it. But the bigger lesson is you have to be persistent, keep doing it, and eventually things click. So PC, HP, remember that, and that is the lesson I have from my life. Chips are used in so many places. Okay, um, these are in your PC. You all know that, right? These are in your mobiles. Okay, these are literally everywhere. Anything that has electronics, some automation, a small or bigger or different side of chips are there. But the biggest revolution that we see in the last 2 3 years, and that is still a very early stage. And the reason I'm setting this for you, because okay, you have another year to take on projects, and then you will get into the field, and this field um, is gonna get crazy in the next decade or more decades and all that. Okay, it just started now. So the chip design has a big contribution in this field. This all came with suddenly when ChatGPT came. Everybody started wondering, wow, that's a new kind of thing that we haven't seen before. And even this stuff I took from ChatGPT, and it's become important in whether you're a student, whether you're a professional, whatever field you are. This type of AI. So there is one traditional AI, which is we call machine learning, right? Um, you you analyze the data. Based on the data, you create a mathematical model. Then for a new data, using that mathematical model, you create an output. That is a traditional AI that has been there for like last 10 15 years. But this new AI, which is called a generative AI, right? And intelligent, smart information, new information is generated using large language models, right? That has revolutionized so many things, so many things. And the key component of that is Again, if it was I was talking to you directly, or there was a way I could get feedback from you, I would ask you some questions here. But this is where you train large language models. Okay, and the size of those models is getting bigger and bigger and bigger and bigger. It takes few months, for example, to train a large language model for a ChatGPT type big models, to train them. And then once those are trained, then you kind of get inference from them. You can real time use them. You can deduct information from them. You can have them generate intelligent information. The two companies I mentioned here, okay, one is NVIDIA and Broadcom. There are so many other examples, but I only picked these one. So these two companies have made remarkable progress in the last 2 3 years. So I've been just given some numbers. You don't need to remember those, but uh, this Nvidia's revenue last year was 60 billion, Broadcom 50 billion. Broadcom's the key division that was responsible for all this revenue generation was their custom ASIC division. They make AI chips, those chips which are used for training, right? For other companies. So NVIDIA, what is it famous for? For GPUs. Suddenly GPUs found its way into training and inference, right? So this is where NVIDIA, Broadcom saw they had the right product for those for the AI market, and things exploded. They got a market share of 4 trillion momentarily, and the Broadcom 1 trillion. Just to give you some idea of these numbers, um, I don't have much time here, but I know sometime remembering 60 billion is tough. I got some numbers there again from ChatGPT. Total Pakistan federal revenue in terms of taxes and levies and all that was 64 billion last year, and our expenses was 94 billion. So I hope this will help you remember those numbers, that the revenue just from these companies where their 97% of the share contribution were GPUs, and those were in the AI field. So the point I'm trying to make here, AI is a big field. All right, now I will get into, okay, we talked about AI. There are so many other applications, right? Now you talk about, let's say we take this motherboard, where the chips are. Okay, you probably guess is that there's your CPU, that's the main chip, right? Then there are chips on your memory slots, memory cards. Okay, this is your graphics card, so you have chip there, and there are so many other chips there, right? So now I want to give you very briefly, I can spend a lot of time on it, but considering time, I'll tell you that within a chip, what are the key components? Now, this will be important for you. These are the chips that I have designed at Intel, and I will now see even with customers as a Cadence employee. And the chips has these different components. Okay, they have CPUs. Again, I can explain you what is CPUs and all that, but there are all kind of CPUs there. So there are CPUs. There is a memory. So your chip has its own internal memory. This is DRAM, the external one. Then chip has a customized digital chip. These are called accelerators. So if it's a chip for AI, you will have a neural processing unit. If it's for networking, there will be networking accelerator. There's a compression. So this chip is, or this part of the chip is to help CPUs. Your CPU is busy doing other things. Somebody moves a mouse and application upon that, but this special hardware is called accelerator. Is there helping CPU so that they can do more heavy load for them. Okay. Then your chip has some analog components. It could be some low speed IOs or high speed interfaces, could be clock generation, voltage regulation, right? So you see that there are different components, and I'll show you in a minute the overall picture. So you have some analog and mostly the digital components here. So if I draw it, this is a typical chip. that whether it's an Intel client or Intel server or even on Broadcom or other companies, you see a similar chips. So your chip is here. Okay, it has a lot of CPUs. Now CPUs can be smaller CPUs, bigger CPUs, and then they will have an accelerators, multiple accelerators. I just created an example for you. Then your DDR interface, right? Then they have clock generation. Then some IOs like maybe to mouse, to display, and hard disk, stuff like that. Then you have high speed. These PCI, for example, I drew them. These are high speed interfaces. All right. So a chip is typically made of this one. So again, look at Intel, some of the chips, and I'm not going to explain you all that. Every chip has a code name within Intel or within any other company. I spend most of my time with Intel, so I give examples from there. So this is a this chip came in 2022, third generation chip, and this was a Raptor Lake, is code name. And inside we had within a packet two chips, but this is one of the main chip. Okay, and if you look at this one again, I don't intend to explain you everything here, but there are a lot of CPUs and a lot of different type of CPUs. There are GPU, which is accelerator, and there are a lot of other agents there, and they are connected all. They communicate through this. This is a picture of that chip. This is a pretty big chip there. How many transistors are in these type of chips? Any guess?
A few billions.
Few billions. Yes, that's true. So few billion transistor, and nowadays another concept is coming, 3D IC, but maybe I can explain you some other day. So this is a typical chip. All right, largely digital, but it will have some critical places, your analog part too. Okay. Now, if you go further, there is another thing. How many people understand the difference between ASIC and FPGA? So, ASIC and FPGA. I wanted to explain this to you quickly because I think this will be very important for you. An ASIC is both are chips finished. They are designed, they are verified, and they are fabricated. And I'll talk some of those steps later on. But the key difference between ASIC is once the chip comes, like this chip, this is an ASIC. Everything is designed already done and dusted. CPUs can be through software, through the memory, they can do different job. But basically, you cannot change the hardware of this. FPGAs, on the other hand, which is one here, their hardware can be reprogrammed. You can change the hardware. Some of, not everything, but some of the interconnection of some of the building blocks you can change. So typically you use it for prototyping type of that because you can get few chips and make a boards on them. These chips, when fabricated, they come in millions or at least thousands, right? I'll hit FPGA again in a bit. Again, I'm not going into too many of the details, but maybe some other day we can do that. So now, chip, you guys are following me, right? Hopefully, I'm not giving too much information, but chip is a business and it's an expensive business. Okay, like in every business, you need to have a product. You're making your own chip, so that's your product. You need clients for that. So the way everything starts is you have an idea, you do market search just to make sure that the product that you're bringing is there is definitely a need for that in the market. Then you want to sell to clients or customers on a given price. Your cost in building that chip is it's actually called your cost, right? And the difference between price and cost, I mean, I'm simplifying here. Let's say this instead of gross margin, just your net income. Your gross margin is your net income because in cost we will put every cost in it. Okay, cost is what your marketing, your offices, and all that other related expenses. Machines, you need machines, you need hard disks, and all that. Prototyping, you need to go prototypes and etc. But the design, the cost that I want to touch a bit, design cost, okay, has three components. The first one is human resource. You need designers, you need people like you. Then you need tools to design your chip. Then once you design the chip, you need to send it for manufacturing. So all these expenses typically are in millions. Now, tools, you're probably wondering, okay, you have Cadence licenses, I work for Cadence, and you are using them. Then another big company is Synopsys. Then also here a lot is Siemens EDA. There are a few others as well, but these are the top names. Manufacturing, okay, you might have heard TSMC. These are manufacturing companies, except Intel here. They don't do design. Their job is, and NVIDIA sends them, AMD or other company, they send them their finished design and they manufacture them. TSMC, Samsung, Global Foundries. Intel has also started its foundry for others, but in the past, mostly Intel was using its manufacturing for its own design. So Intel has unique position as a design and foundry. This is Samsung Foundry. All right. And this is where we talk about what kind of transistor technologies, 2 nanometer, 3 nanometer, 5, 7, and other. So you got an idea, right? You need specialized tool. You need to manufacture them. And then these are, very expensive things. And here we come in under HR, human resources. That's where you come into the picture. I'm not considering the marketing, software, and other people, the designing, the hardware design part. Any questions so far? Any burning hard questions, something that you're stuck, you're not able to understand? Okay. So here I'm going to give you a very brief overview. Okay, very simple 50,000 feet overview of it. So you have a chip, you want to design a chip, you need an overall architecture. That's not what I wanted to do. Okay. So architecture overall. Architecture means how different building blocks, different building blocks you need to have. Architecture can also mean if you're picking a CPU, what kind of instruction set it has. But anyway, think of that. You have different pieces, what different pieces need to be, what features you need to put in so that when you build it, it's sellable, blah, 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 right? Then microarchitecture means you have a high level architecture. Now you need to convert that into smaller building pieces. Okay. Once you have smaller building pieces, like you have a CPU, you have GPU, you have media engines, you need to have IOs, you need to have clock generation, all those things that I mentioned to you, right? Now designers need to build those individual components. Now, as explained you, there are some layer analog pieces and there are some digital pieces. So analog components, which is the expertise of Rashid's lab, um, they are on a smaller number of transistors, but they're very hand made, very customized solutions. Schematic, layout, the whole style of analog design is very different than digital design. That's what you guys need to understand. Okay. Analog design is different. The whole methodology, tools, and everything is different than digital design. So you have in your chip both digital pieces, both analog pieces. The analog is done this. Digital, mostly I talk about, there could be a customized digital portions, which are more or less like analog. But the majority of the chip is where you write the hardware in what we call RTL, register transfer logic. You use system verilog, verilog, VHDL. You design them, you validate them, and then you convert into this RTL, which is system verilog, into gates into transistors, and eventually you create a transistor version of it. This is called physical design. This is my area of specialization. Okay, so and then once you have digital components, analog components, you need to integrate them at the top level, chip level. This is again in those big chips, we do it with RTL, system verilog, and different components come in. And then we integrate them in, we physical design them. So these two pieces come here again. but at a full chip level. So when everything is designed, tested, a lot of feedback happens back and forth. Once we are ready, we send the database to fabrication. This is called taping out. In olden days, there people used to put it on a tape and give that tape database to the fab, but that doesn't happen. We just click a button and it goes to the fab. So fab fabricates it typically those bigger chips 2 months to 3 months it takes, and once they're done, they come back and we validate everything. Okay. Any question on this one? You guys are very quiet. All right. Okay. It's fine. Let's move on. If you don't stop me, I'll keep talking. Okay, so now comes to a very important section, your careers. Okay, your final year projects, where you're gonna start working for, what area. So the architecture, microarchitecture, I remove from here for you guys because when the designers come, they first start, majority of you will come into these areas, individual components, analog and digital. Okay, so in digital, you will do an RTL design, RTL verification, where you will be working with system Verilog, VHDL, and all that. You will validate. It's not about designing. So basically, what it is, you create a design. It's a logic design. You must have studied logic design, right? So in terms of gates, you create your logic digital system. You design a digital system. And then once you design that digital system, you code it in system Verilog or VHDL. Once you have that, and that is just a higher level description. So using physical design tools, like from Cadence, there's Genus, there is Innovus, from Synopsys, there is IC compiler, design compiler, fusion compiler. Using those tools, you convert that into basic gates, which called standard cells, and then those standard cells are eventually layout and all that. So this area is auto. You deal with millions and billions of transistors. There is no way you can do that in handmade way or hand drawing way, right? You have to rely on tools. This area, I'm not expert, even though my master was on it. I haven't worked on this field, but Rashid and his lab is they're super good in this one. So in this one, you have a different way. You create a schematic, you simulate it, you verify, then you generate layouts, you verify, and all that. Okay, so overall, it's similar things to you verify, but your approach is very different. So within these areas, you can come as a design person, you can come as a design and verification person, or you can come as a verification person. Then there is typically another area, design automation. You create a lot of these things are such that you create based using scripts. You create automate some steps so you don't have to manually every time do it. I think that's the best way I can explain. But this is digital, this is analog, and you guys will be entering into these fields. Now, one thing I do want to, and I'm bringing this back, this is where my final year thesis was. And this FPGA, even though they are mainly for prototyping, and they're used heavily in defense as well, um, uh, I'm not going into their pros and cons. Maybe some other time I can come and explain that to you guys. But once the FPGA chip is there on a board, you can reprogram it. And when you create a hardware for it in the tools, it's very much like this RTL. Okay, so a lot of these are easier to get. So academia and universities, they have a lot of these ones. So one good thing with these one is if you know the RTL design and verification that you typically do for programming, these one is very identical these. Of course there are some differences, but I think typically for people to go from here to there is not that difficult. Physical design methodology can be a little different there. So even though it has a some physical design, but this physical design will be a little different. But I think if a lot of you guys don't get opportunities for here, but at least in your final year, if you have interest in this field, you can use FPGA. Okay. Here, Rashid Labs can explain you a lot more what different areas and components are. Questions? So opportunities. This picture I took from a WhatsApp group. Lady Sundar, she has summarized this pretty well. Um, Now, when I left university, we had what enabling technology. We had another company and our logic. I don't know if they still exist or not. Um, and those were the only two companies, if I remember it. Um, and then later on in 2002 3 defense started investing a lot. But now that's a great news for you guys, right? Look, there are 19 companies. Even there are five, six, seven actively hiring or getting engineers into it. So you have a lot more opportunities to go into and get your hand dirty, learn things, get the practical experience and all that. Okay. So you can find this picture and you can approach different companies there for their opportunities. So you have a lot more opportunity in this field. And I think the salaries, starting salaries are pretty good as well. So, I was from a low middle class. For me, my salary and how much salary I get, that was a very important thing. I'm sure that's important for everybody, but you guys can get a good salary from these jobs. But let's see, even after a few years working there, or if you don't get opportunities there. All right, what was that? So there are a lot of opportunities outside. And I gave you example of Nvidia and Broadcom, but there are so many other companies, so many smaller and bigger companies, not only in AI, because chip design is not just AI. I just use an example of AI, but there are so many other fields where chips are produced, fabricated. So many opportunities are outside. But for that, you need to leave Pakistan, right? And the best way I tell people, there are people like me who really wanted to leave Pakistan, go work abroad, better money, but could also be experience, right? You work in developed countries, you want to do a master PhD from developed countries. So I think those are really um, good things. I mean, for you and also for the country eventually. So best way is what I've seen. Even though there are some stories from Pakistan, people went to Europe as well, but at least U.S. you really have to come for education. Um, the city I am living, it's Fort Collins. There's a Colorado State University is here, and I do see students, especially in the from Faisalabad University for the this livestock or agriculture related. A lot of students come here for masters and PhD. They get this Fulbright scholarship. I don't know if Trump has removed them or not, but talking to them, there are still opportunities there. Contact the professors here, um, find scholarships, find some assistance here. You can once you come here, you can find some job opportunities as well. I don't see that many people, especially in our field, come to US. And I think there are so many opportunities in US, but the first part is you need to come over here. So, and education is the best way. All right. So I think my last slide is, and it's 57. Sorry, you guys started it late. On my channel, the things about digital design that I talked about, right? That's where I cover. So my focus is eventually physical design, but I tell you what, and you guys are finishing your third year and going into final year. And I'm surprised that how many students, even though they have taken courses on logic design, but they struggle to design a digital system. And I think I was not an exception. It's a long story. I'll skip that. But key thing, if you want to go to digital system design or RTL or this skill here, is super important. That given the knowledge of simple gates, little bit complex gates, combination circuits, sequential circuits, you should be able to design a hardware even on a paper with some block diagram or some detail or less detailed pictures, how to solve a problem using digital system. That skill is super important, and that is the base for a good physical design engineer, good RTL design engineer. So spend time there. I had a playlist there, and I'm gonna refresh that playlist. I'm gonna add more things there pretty soon. So stay tuned, and any questions or anything come anytime, you can ask me on my channel or LinkedIn or WhatsApp. So, folks, that's it. You have been quiet, but I'm okay spending more time above the hour if you guys have questions.
A question from Mujahid Bilal. Sir, can you explain how UVM chip verification relate to the chip IP verification using system Verilog?
Yeah. No, that's a great question. So if I intentionally didn't mention some of the things there, but within RTL, there is, I said, design and there verification. So design, if you at your level, at your final year projects level, at your understanding, when you create a hardware and system Verilog, you can create test benches, a verification plan for that using system Verilog. You don't need to use UVM methodology, right? But when you go in a production environment where join a company, they will be having this. They, I'm not expert in that area, but what I heard is a lot more automated. You have things are much more defined in terms of how you can apply a stimulus, how you can verify the outputs. So that UVM thing comes in this picture. But again, for you guys, it's okay if you don't worry about UVM. Just use a system Verilog or Verilog, and using system Verilog or Verilog, verify the whatever hardware you build. That should be enough for you. But yeah, UVM is pretty advanced. It's pretty common. It's more rigorous testing that is available with that.
Thank you, Rashid. The next question is from Mohammed Shoaib Server. Sir, what is difference between PD and layout?
Oh, okay. So PD is physical design. All right. So physical design, remember this. Physical design is overall what is the thing that you want from physical design. The output needs to be transistor located and interconnected, which is also the layout from this one, right? But the PD, in order to get to that final stage of layout, PD is an overall method. It has so many components within this. So you have first from RTL, you come into synthesis. This is called synthesis. You convert into gates, and it does a lot of optimizations. Then once you do that, you place your so output is cells or gates. Okay. Then from synthesis, you go into placement on a chip. That means all those cells are placed. Once those are placed, you build a clock tree, and then after that, you route your design using two. The output of route is your layout. Layout means your transistor laid out and connected to each other. So physical design, this whole thing is called physical design, and layout is the final output of it. And these are different stages through that. So typical, we convert into this smaller blocks. So you will have how many cells you will have? You will have few million cells, and each cell typically think of an AND gate. So it will be like two times that will be the number of transistors in a simple simplification. Make sense?
Thank you very much. Perfectly makes sense. The follow-up is, so this means the from Shoaib server that PD are auto-generated and the layouts are hand-generated. So this is a question.
Oh, all right. Okay. So, yeah, if you think of layout, so I call even the output of PD as a layout. But yes, it is an auto generator layout. So, since you are dealing with millions of or billions of transistors, there is no way that you can create that hand layout manually, right? By putting this transistor connecting this transistor. So, for that, we have tools which generate this layout. But we still call it a layout. But you are right, we call it auto, place, and route. But here, these are few transistor, and it has to be very customized because it's it is a different world, this analog world. But this is also layout, but it is hand generated layout. So you don't have the same methodology here, but output in both worlds is called layout. Still layout. Is the way you come up with the layout is different.
Thank you very much. There is a question from Sadiq Akbar. What area to go for in the design? Is
Hmm.
it critical among ARM and the RISC-V when start a design career in IC design from industry perspective, especially for AI accelerator? Let me simplify the question. This means that which architecture is more relevant nowadays, ARM or RISC-V? And secondly, from IC design perspective, when the AI accelerators are there and they are designing automatically the chip, so what is the AI effect on these both learning curves?
Hmm. Okay, so let me address your first question. So, risk five has a big, definitely flexibility that it's an open source, right? You don't have to pay the fee or pay the premium to, for example, to ARM or Intel has x86, so you're not paying the money to them, right? You can follow that instruction set architecture. You can create your own hardware and you can use it, right? That's the big plus of that. But how much is that in the AI right now? There are a lot of startups. Okay, one of the biggest startup I've seen in that area is Tenstorrent. Okay, Tenstorrent, headed by Jim Keller, who was previously at Intel, and before that, was Tesla. Is a very good speaker. You guys can search YouTube for his lectures or for his presentation, and they are coming up with a very different architecture, and they're trying to disrupt and to take some share from GPUs. So there has been a lot of work um, from different instructions architectures, the how they can disrupt the market that is offered by NVIDIA. Uh, but so far we haven't seen it much. Intel x86 that AMD uses, I think they are the, if I say after, as of now, after NVIDIA in the AI market, AMD is more successful. But others are not there yet. We will see how the companies like Tenstor and a lot of other AI startups, so much investments happen in those architectures. Let's see. It will take another couple of years for us before we can say if those are successful. So, okay. What was your second
Yeah.
question, Raisa?
The second question, I will mix two or three questions together now.
Sure. Sure.
There are multiple questions, so now let me allow me in the mixing. The one question you already answered. Second question is from Shariar Kracha. It's a short question. Spartan 3 kits are still valid or not? Are they updated for F5Ps?
Okay. It's been a while since I work on FPGAs, so I don't know much about it. I'm sorry.
So if you allow me, I can answer this question.
Sure. Sure. Go ahead.
Spartan kits are not irrelevant at all. Spartan kits, as for the FIP, they just are the means to test the Verilog code so that it's ready for the synthesis. What we do is usually we put the Verilog code, do the simulation. Simulations are very slow. We simulate for few tens of cycles, and then when the Verilog code is we think working, we put it in the FPGAs just to see in the real time that code is flawless. So then the code is ready for the synthesis. So FPGA of any kind are relevant all the time if they are able to handle the complexity and speed of your code. So for the small projects like your final year projects, Spartan 3 kits are very relevant even today.